n log n, then you can show that all the bins have a size that is within some small constant of 1. Okay. So then your intuitive load balancing assumption works. So, right. So if this is the case, then much better load balancing. So this is just something to note, that if you have many more balls, then they become uniform. This is what you would expect, because because now the expectation in each bin is something like m by n, and if m by n is somewhat large, you expect that everybody will be around. Okay, so we'll see how to formally prove these kind of things today. Okay, so let's not do that now. Okay, so another thing that I thought I should just mention is, like many times, you encounter this situation where you have n items coming in and you have n bins, and you want to allocate them as they come along, right? So we just saw that if you did uniform allocation, then it's not really good. Okay, so there are many bins that are empty, and there are some bins that have a pretty high load. Now, what people have considered is this very simple strategy, which is instead of sending the ball that you get to a random bin, what you do is you pick 2 random bins uniformly at random, okay, and you check which one has fewer balls. Okay. So you make, when a ball arrives, you pick 2 random bins and send it to the one that has the smaller of the 2. Okay. And very surprisingly, this turns out to give a maximum load of log n, which for all practical purposes is usually constant. Okay, so it's just it's a very, very slowly growing function of n. Okay, so it turns out that even if you do like 2 choices and you always send to the smaller of the 2, so the solution you get is much more load balanced. Okay, so this is often done in practice when you are, like when you get a search query or something and you have a bunch of machines, you want to figure out which one to assign it to, right? So instead of doing uniformly random assignment, what works much better is if you query 2 randomly chosen machines, you ask them how busy they are, and this is a short protocol, right? Because it's just like a constant communication, and assign it to the lesser of the 2. This results in a much more load balanced solution. Okay. So I just thought I would mention it. It's proving this is actually quite difficult. Okay, so this was only shown in '91 by Broder and others. Yeah.
So if you are making a random choice of which bucket you want to assign that element to, are we like breaking the assumption of a deterministic hash? Like, does it mean that if I have the same element x and I hash it twice, it will go to 2 different buckets?
Oh, when you do this 2 choices stuff? Yes, in principle, yes. So this is often used when items arrive online. So, if the same thing comes a second time, then you're right. In principle, you could be assigning it to different things. But but it's not used in that setting. It's often used in kind of the search query type settings where you do one thing and that's it, right? And if it comes again, you repeat this. Okay. Yeah, but that's a great question. Okay, so this is not very useful in producing a hash function. Okay, so yeah. Okay, so was the question clear? It was an interesting question. Okay, so these are just some parting thoughts about hashing. There's a lot of literature, and you'll see a little bit in your homework about these the two middle things. Okay, so those are somewhat easy to argue for. So that's some thoughts about hashing. And all right. So the next thing I want you to do is estimation. Okay. So this is another very canonical application of randomized algorithms. Right? And the basic question is this: you have a population of people, and let's say each person votes R or B, okay, and red or blue, and you want to predict who's going to win without actually asking for everybody to vote and collecting these things. So this is what surveys and everybody does, right? Sometimes people do it wrong, right? So this is but yeah. So the question is, how do you predict the winner without actually asking everybody to vote? So that's the basic question. And we all know the answer to this. The answer is to uniformly sample a small number of people and ask them for their votes. And the empirical, and in that sample, whoever runs is somebody you predict would be the winner. Okay, so this is something all newspapers, everybody does, right? So the answer to this is sample n of people. Okay, ask for their votes.
Is being recorded. It's
Output.
yeah, I think so. Say, should I check?
Okay. So you look. So you take a uniform random sample of n people from this, and you ask for whom they vote for, and you output the winner in the sample. And let's assume that everybody answers truthfully when you ask them for whom they vote for. Okay, so in this simple situation. So now the question is, what guarantees can we get for this system? Okay? Like, how would you analyze, or how would you try to reason about the probability that the winner in the sample is indeed the winner in the whole population? So is the formal question clear? That so we want winner in the sample.
10 minutes.
To be equal to
We need to click save.
winner
Close it
in the
and
whole population.
tell us to
Okay, so that's the goal. Okay, that's the goal of sampling. Right? And what would you expect these kind of things to depend on? Actually, just to get some intuition about how you would go about analyzing this, right? Yeah.
Signs of n, so if I only ask for my mom, then it's going to be simple.
Okay. Right. So things that ought to matter. Right? Okay, so one thing I already said is everybody answering truthfully. And also everyone whom you ask should actually answer. Okay, so that's one of the other things. Apparently this is one of the reasons usually election predictions can go wrong. It's like people either don't answer truthfully or they just choose not to answer if they don't want to. So truthfully, and also the number of okay. Anything else that should matter?
I guess it would matter how close they are in proportion.
Okay. So we're going to yeah. So the margin is what matters, right? So So this is how close the truth. Okay, so this is great. So these are all somehow the reason I'm listing these out is because somehow all of these should show up in our analysis. Okay, so this is when you're thinking about formalizing things, you should first think of okay, what should intuitively show up in our bounds, right? And these two should somehow definitely show up in our bounds. And yeah, so what is the final thing that you think has to show up in our bounds? Yeah.
Do you think the samples should be uniformly sampled? Vastly.
Right, so that is definitely sure. So in the setup, we also need sampling to be truly uniform. So this is another thing that is very hard to do in surveys that people conduct because it's hard to reach out to somebody in remote places and stuff like that. Okay. So that's important. Okay. So the other thing that I wanted to say is the confidence in our outcome, right? So there is always this element of probability involved, right? Like unless we truly sample the whole entire data set, somehow we should, we would not be 100% confident that what we are producing is the right answer. Okay, but of course, as you sample more and more, your confidence grows. Okay, so that is one parameter that has to show up in all our models. Okay, so there is the confidence in our prediction. Okay, for those of you doing machine learning, this is very common. Right? So this is why you get all these like back type models. Okay, so you have some notion of confidence in your predictions. So, all right. So this is so these are things that should show up in our box. Okay, all right. Okay, so now let's see how you would formalize this. Okay, so let us R and B, red and blue would be difficult for us to think about. So let's just give 0 or 1 as the as our outcomes. Okay, so every person either picks 0 or they pick 1. Okay, so then we can try to mathematically formulate this. So each person choice of 0 or and let's also give some names for this. So N0 is actually, let me write capital N's for the whole population. Okay, so capital N is the entire population. The size of the entire population. And 0 is number that vote 0. And 1 is number that vote 1. Okay. So capital letters will denote the population level quantities, and small letters, small n, will be the sample and so. Okay. So now, the first question is what is the algorithm, right? So just what is the formal algorithm? The algorithm is just choose little n people uniformly at random. Okay. And so in this sample, let small n0 be the number in sample voting 0, small n1 is the same thing voting 1. Okay. And our check is check if n0 less than 0. 1. If so, you predict that 0 is going to win 1. If so, you predict that 1 is going to win and vice versa. Okay, but you can think of this as the question of estimating okay, so let me just write it a little differently. So the predicted winner 0 if 1 is all right. So that's fine. Okay, so this is just this is how you this is just writing in symbols what we said before. All right. So now let's define a random variable which I will call x sub I. Okay. And x sub I is the outcome of the ith person in the sample. So, in the sample. Okay, so we have small n people in the sample. Okay. And this is now a 0, 1 random variable. Right? So this is the ith person in the sample. Okay. Right. So now suppose I ask you what is the probability that xi equals 1? What is the probability that xi equals 1? Right? Small, yeah, why is it, so is it small n1 or capital N1? I guess that is my question.
Capital N1 over N.
Yeah, so why do you say capital N1? Why do you say small?
Because I think we are only considering the sample.
That's fine, but I'm asking you, I haven't fixed the sample yet, right? Okay, so yeah, so this is one sanity check I want to do. Okay, so we haven't fixed any sample, so we are just asking what is probability that the ith person votes for 1. And we haven't fixed the sample yet. So this is just capital N1 divided by N0. So this is capital N1 by. Okay, and so also probability of xi equals 0 is the same. It's similar. So this is some very basic quantity. And again, right? So can you write little n0 as some sum of random variables? I just want to do some basic random variable exercise, so that's why I'm asking this. Okay, so what is little n0 or little n1 in terms of these x variables?
Began to choose small n.
No, little n1 is the number in the sample that are voting 1. So what would it be in terms of these capital X random variables? Can you write it in terms of, like, capital X is the outcome of the ith person in the sample. Yeah, so this will just be the sum of the capital X's, because that's how, capital X was defined to be 1 if the ith person voted 1 and 0 otherwise. So capital X, n1 would just be x1 plus x2 plus xn, and so also n0 would be n minus. Okay. And formally speaking, both small n1 and small n0 are also random variables because they are some quantity that depends on the sample output. Alright, so this is, I just wanted to do some basic sanity check. Alright, so now, and the reason I wrote these is also like these are random variables that take some 0, 1 values, and so we can ask about expectations of these quantities. Right? So what is expected value of xi? What would be the obvious expression for this?
One sample proposition xi equals 1.
Yeah, so this is a random, this is a 0, 1 random variable. So this is 0 times probability that it's 0 plus 1 times probability it's 1. So this is 1 times. So this is just random. Okay, so this is the expected value of x. All right, and what is the expected value of? Yeah, now we can ask what is the expected value of n1. So this is a sum of random variables, and so you can now use linearity of expectation. So this will just be small n times. The reason I'm just spelling this out is because, in some sense, all we are asking is so we have this n1 whose expected value is this. Okay, and you have this n0 whose expected value is n times n0 by n. Okay. And the comparison we are doing is we are comparing little n0 with little n. And if both of them were very close to their expectation, or if both of them were basically equal to their expectation, then comparing little n0 and little n1 is exactly the same as comparing capital N0 and capital N, which is exactly what we wanted to do, right? Like we want to know who wins the overall living. Right, like in the whole population. So in some sense, to analyze this sort of a thing, so what we need is some way. So what we need is a way to argue that expected value of n1 is actually, or yeah, maybe we could say n1 is actually close to the expected value. Okay. So, because if n1 was exactly equal to the expected value, and n0 is exactly equal to its expected value, then you are in great shape, right? Because then you can say that, comparing n0 and n1 is the same as comparing capital N0 and capital N, which is what you want. So this will be our way of analysis. Okay? And this is exactly what I was saying before, right? Like we wanted, like Markov's inequality, as we said, is some way of stating this meta theorem that random variables do not deviate too much from their expectations. And now we want a much stronger, much more fine-grained way of saying the same thing. Okay, so this. Yeah, let me pause here and see if you have any questions. So basically, would you guys agree that what we essentially need to do to argue about whether this procedure is correct or not is to argue this point. So that's so that's the main way you formalize this question. comment. Somebody would like to phrase it differently, that's you're welcome. Alright, so let's let's go about this. Okay, so this is what we said. And yeah, I still haven't worked with this part. Okay. Okay, so what you need is a way to actually argue this thing, and for that, what I would like to say is this: it's define this quantity called estimation error. So this is estimation error, which I would like to say the fraction of votes and like 0 received, or let's say 1 received in the sample minus the fraction of votes that 1 received in the population. Okay, so this is another way of capturing the exact same quantity. So what is the fraction of votes 1 received in the sample? This is n1 divided by n. And minus the fraction of votes in the whole population is something like n divided by n. Sorry, n. And using and this expression is basically so you can write this as n1 divided by n minus the expected value. So yeah. So these are just equivalent ways of writing this. Okay. All right. So this estimation error is a quantity that we will discuss, and that is basically the difference between the value you found for n1 minus its expectation. And I'm scaling it by this small n, which is the number of samples we take, because you might as well do that. Alright. Yeah, and I wanted to basically get to the kind of guarantee you would hope for this sort of a thing. Right? So the kind of guarantee you would hope for is you expect the empirical mean, which is this quantity minus this quantity, to be small with a very high probability. Right? So that's when you can be sure that your sampling succeeds. Right? Because you want, so let's take a more concrete example. Okay, so when would so if n0 is approximately equal to expected value of and n1 is equal to expected value, then you know that the sample is representative of the whole population, right? So this is what I just argued. Now the question is, if these are only close, right? So how close do they have to be before, for you to be able to conclude that your prediction is correct? Does that make sense? Yeah.
Shouldn't we say how good we want that prediction to be, and what is good for us? The
Yeah, exactly. So I want to get that, and that I want to say depends on the margin. Okay. So if capital N0 and capital N1 go very very close to one another, then I would like to argue that these two quantities must be really really close for us to have a reasonable guarantee. Okay. So that's something I want to get at. So, right, so, okay. So what we know is that if expected value of N0 is exactly equal to N0 and so on, then, okay, what we just argued. Okay, this is from their expression, from the corresponding expression. Is that if N0 is equal to this and so on, then sample so the sample winner is the same as the true. The sample winner is the same as the true. Okay. So this we have just argued, right? Because if these because the expression for expected value for N0 was this expected value N1 was. So if these two were so if N1 was exactly equal to the expectation, N0 is exactly equal to this one. So now, okay, so what if N0 equals 0.4 N and N1 equals 0.6. So 40% of the people vote 0, 60% of the overall population votes 1. Okay. So now, when will our prediction be correct? Right? Like we were sampling small n people, okay, and of this overall thing, of this overall population. We are asking when will little n0 be, and if little n0 is less than little n1, then our prediction is fine, right? Because then we would be predicting the right one. So in this case, our prediction is right if and only if little n0 is less than little n. Okay. And of course, what is expected value of N0 in this case? Sorry. Somebody seems to be saying the right thing, but it's not. 0.4 times. Yeah. So it's 0.4 times what is, I guess, the confusion is 0.4 times small n. Small. Okay. So this is 0.4. Okay. Good. So now, right. So now, as long as the actual N0 is strictly less than small n by 2, our prediction will be right. Okay, so this is, maybe I read this. Do you all agree with this? Because of course our claim is right means that we predicted that N1 that 1 is the winner. So that happens if N1 is more than N0. Small n1 is more than small n0, which essentially runs because their sum is 1 is small n. It means that n0 is smaller than small n. So this is what we have. Okay, so therefore, our prediction is right, if and only if, and this is also an if and only if. Just to be mathematically accurate, both are. Prediction is right if and only if n0 is less than this, or equivalently n0 minus the expected value of n0 is less than 0.1. Okay. So this is what I want to get at, right? So we know that so we know that the expected value is 0.4, and we are right as long as it's less than 0.5. Therefore, you want this difference to be less than 0.1. So the next question I want to ask. So actually, yeah, any questions about that? So if your n0 was that and n1 was that, then our prediction would be right as long as this is true. Right? Okay. So now I want to ask the question: what if in the true population, 49% of the people vote for 0 and 51% vote for 1? So in this case, if you did the exact same reasoning, right? So the first step, you will have expected value of little n0 will be 0.49 times small n. And this is still the same statement, right? So you still want the empirical prediction to be the same. And so our prediction now would be right if and only if. Therefore, in this case, right, if and only if zero is less than now 0.005, 0.01. So now you need, sorry, small. So now you need your estimate of this n0 to be really close to its expectation. And this is where the margin in the true population comes into our analysis. Okay. So this is what we will try to analyze. And our goal for today is to be able to analyze the probability of events like this. So the goal for today is to ask if we take n samples, what is the probability that n0 minus the expected value of 0, the absolute, okay, actually you don't need the absolute value in this application. There are some failure like what you would want, right? Like you want to say that that you want to have a confidence in your prediction. So that's what we'll get at. So now the first question to ask is, does Markov give you anything? Because that's one bound we know to say that a random variable is close to its expectation. Right? Because we are ultimately what we are arguing about is this random variable close to its expectation? Right? So is this random variable called n0 close to it? So let's see. Okay, so let's for now fix the example of capital N0 equals 0.4n capital. It doesn't really matter, as you'll see. Okay, but let's for concreteness, let's fix that set. So now what does Markov tell? So in this case, we are interested in the probability, something like this. So we want n0 minus expected value. So be less than 0.1. Now Markov, you can use this. So what is Markov? Let me just write it down. Probability that n0 is more than t times the expected value of n0 less than or equal to 1 by 2. So this is what Markov tells us. And in this case, what do we want t to be? Well, I mean, what should t be for you to get that quantity? Sorry? 10? Well, 10 is too high, right? So actually, why do you say 10? Well, but it's close, right? So what you want is you want to write this little n as a function of this expected value of n0. Okay, and but that's why I'm sticking to this example, because you need these quantities, and you can see that this is expected value of n0 divided by 0.4. Okay, if you think about it a little bit, you'll see. Yeah, because expected value of n0 is 0.4, small n. That's right. Alright, so this is that. So then this is like asking, when is n0 less than expected value of n0 times 1 plus 0.1 by 0.4. So this if you think about it, is just 1.25. Just to be, or if you like it, then just like 5 by 4. Okay, so this is the problem with numeric examples. Okay, so you have to, I would say just believe the calculation I'm writing. Okay, so that's not important. Okay, so you get some numbers. Okay, so you succeed if n0 is smaller than 5 by 4 times expected value of n0. So if you want to bound your failure probability, so to bound your failure probability, you want to say what is the probability that n0 exceeds, and that you would like to be small. If you just use Markov, you get that. So you use this inequality. So you have to put t equals 5 by 4, and you get failure probability is less than or equal to 1 divided by 5/4, so which is 4 by 5. Okay, so this is, I mean, this is an okay failure probability, but it's by no means something that you would be happy with, right? I mean, if somebody told you, hey, here's this estimation procedure, it works correctly with probability 20%. Like the failure probability, I can bound it by 4/5 is like 80%. If somebody told you your failure probability is at most 80%, would you be happy? So probably not, right? And so this is a bad bound. Okay, so and actually the reason this bound I think is very bad is because there is no dependence on the number of samples you're doing. Okay, so if your small n was a million, or if small n was 1, you get the same guarantee, right? So this is often the case when you just use Markov. Okay, like you don't get like an advantage if you pick more samples. Okay, so that's this one Markov. So now let's try to see how you can get some dependence that depends on the number of samples you make. Okay. So, but is the problem with Markov clear to everybody? So you get some bound, but it's usually not as nice as you would want. Yeah, but it's fine. We can hope to improve it because, as I said last class, Markov is almost never optimal. So you can hope to think more and bigger. Okay. So, all right. So let's do that. And the question is, how do we use the number of samples? Okay, so that's the key question that we want to use. It turns out the key is to look at the variance of this estimate. Okay? So if you take in machine learning, you would have seen the term variance show up a fair amount. Okay, but I won't assume you have. So let's try to see what that is. Okay, so firstly, I will define this abstractly. Okay, so what is the suppose x is some variable. Actually, yeah, maybe someone can define. So what is the variance of x? Usually people write as VAR. Maybe people have heard of standard deviation. What is standard?
The expect value of x divide subtract expect value of x and square root.
Okay, so this you should go back to your early statistics classes or early probability class. Yeah.
How is variance going to really be applicable in the situation where you have your two populations of either 0 or 1, so there really isn't going to be any.
You will see. Yeah, that's a good thought. You will see why it's relevant. Okay, I mean, so I guess the variance is relevant because the sampling procedure has some variance. Right, so it is 1 with a certain probability, 0 with a certain other probability. So it's inherently a random process. That's why there will be some variance in that. So yeah. Alright, so the variance is defined as follows. For any random variable x, you can define variance as the expectation of a different quantity, and this quantity is now x minus the expected value of x whole square. Okay, so this looks a little tricky the first time you saw it. You see it because there's two expectations. Okay, so think of I mean, if you just think of this random variable. Actually, yeah, so to people agree this looks confusing because it used to me the first time I saw it. So, but I don't know, maybe it's. Yeah, because I mean, this inner expectation, you should just think of it as a constant. Right? Like x is some random variable, expected value of x is something, which is just the mean of that random variable. Okay? And now, if you denote expected value of x by this mean, which is mu, then all we are saying is, now I am looking at this new random variable y, which is defined to be x minus mu whole square. And I am looking at the expected value of just that random variable. So there's nothing very serious going on. This is just the definition of all right. So this is So this is how you define the variance. Okay. And one interesting property about variance is that if you have the sum of a bunch of random variables, so its variance, so if your x is equal to x1 plus x2 x xn, then variance of x is equal to the sum of the variances as long as they are independent. So this is generally not true, and you can imagine why. In your homework, you will see an example. Intuitively, they have to be correlated if this calculation has to break down, right? But you will see. Doing this calculation, I think, is useful. Okay, so is equal to variance of x1 plus variance of x2 plus variance of xn if they are independent. If xi are okay, so this is a slightly non-trivial fact. I mean, you have to expand it out, and it's a little bit of a mess. Okay, but you just have to plug this into the definition, use linearity of expectation for this, and so on. So and then things product out, and all the cross terms vanish. So it's a simple enough proof, but it takes some proof. Okay, so that's so this is a simple fact. All right. So now, so these are, this is basic property. And this is the definition. So if you haven't seen variance before, these are the two things that you should know about variance. Okay, so that's the definition. This is one basic property. Okay. So, all right. So why is variance useful? Okay. So what I would like to now introduce is this thing called Chebyshev's inequality. So all concentration inequalities are named after Russians. Okay. So we saw Markov, there's Chebyshev, we'll see Chernow. Okay. So that's a coincidence. Actually, it's not a coincidence because they're all descendants of this Kolmogorov school of probability. So that's the reason. Because there's so many special names. Okay. But anyway. So what is Chebyshev's inequality? So morally speaking, it says the following. It says that if a random variable has low variance, then Markov can be improved. Okay, so that means that the random variable and its expectation are much closer than what Markov implies. Okay. So that's roughly the message of Chebyshev's inequality. And the way it works, so let me now write the statement. So the theorem is that let x be a random variable. This variance equals sigma squared. So variance is usually denoted by sigma squared. Sigma, which is the square root of the variance, is often called the standard deviation. So this is just something to tell you. Variance is sigma squared. Then probability that x minus the expectation of x as is more than t times sigma. This is less than or equal to 1.t. Okay, so this is what Chebyshev's inequality says. Okay, so you've got the random variable, and you look at how much it deviates from its expectation. So note that this is quite different from Markov. Markov said, what is the probability that this deviates by a factor of its expectation? Okay. But here it's actually looking at the difference between the variable and its expectation. Okay. So if you'll see quantitatively what it implies in the next in our sampling setting. But this is the difference. Okay, that this actually is the difference between these two. And it says that the probability that you deviate by more than t times sigma. So intuitively it means like t standard deviations. The probability of being more than t standard deviations away is less than 1 by t squared. And this is a much more this is a much stronger bond usually. The standard deviation usually is small. All right. So this is one thing. I don't know if I should prove this or yeah, let me not prove this. Okay, so it turns out the proof is actually quite simple because you can notice that this is equivalent to asking that probability of x minus ex squared is more than t squared sigma squared. And if you define this variable as y, like I did over here, okay, then it turns out that the proof of Chebyshev's inequality is just applying Markov's inequality to y. Okay? So then it's like saying probability that y is more than this factor times its expectation. Expectation of y is what we defined as the variable, sigma squared, is less than or equal to 1 divided by this factor, which is basically 1 minus. Okay. So the proof of Chebyshev is just the proof of Markov, but applied more cleverly to this quantity. And in fact, everything, yeah, I mean, so this is why everybody teaches Markov's inequality, because almost all concentration inequalities are basically Markov applied to an appropriate convex function, which in this case this will be this quantity. Okay, so that's so even though Markov is almost never tight, it can yield good things. Okay, so that's something to know. Okay, but yeah, Chebyshev's inequality as such states this. Alright, so why is this useful in our context? Okay, so let's go back to our setting. Right, so now I want to use this inequality in our sampling setting. Right, so remember in our sampling setting, we wanted something of this kind. Okay, and this is starting to look more or less like what we have in our Chebyshev statements, right? Like n0 is the random variable, and that minus its expectation, we want to bound it by a certain term that looks like this. Okay, so yeah, back to the sampling setting. So there we wanted n0 minus expected value of n0 to be less than 0.1. Okay, and now if we use Chebyshev, I mean, I still haven't computed the variance of n0, but let's say I can compute it. Now we are using then we will get probability that n0 minus the expected value of n0 is more than 0.1 n would be, okay, so if you, yeah. So I want to get a bond of this kind, right? And then I have to think about what is the variance and how does this term relate to that variance. Okay. So that's what I have to think about. But let's, so for that reason, let's assume that I know sigma squared and 0.1 n was something times sigma squared. There was some alpha times sigma squared. Then you would get that this is probably a little more than alpha times sigma squared. Less than 1 gram. Okay, so in some sense I've got to evaluate what the sigma squared is for this for the random variable n0. But now remember how we defined n0, right? So n0 was just, that's why we did all these initial exercises, which is n0 was just something of this kind. Okay, so it was a sum of, I mean, if you had worked with n1, maybe it would have been even cleaner, but yeah, so n0 was just a sum of these 1 minus xi variables. Okay, so this is the sum of that, 1 minus xi. So this is just a sum of these basic random variables. And I told you that if you had independent random variables, then the variance just adds up. Okay, so that's the rough idea. So the idea is to now use the fact. Yeah, I guess we are out of time. We have to go to this talk also. But the idea is to essentially compute this alpha. And it turns out that this 1 by alpha squared will be some term that is diminishing with n. Okay, and that's the nice thing you get with this kind of form. Okay, so we'll do this next class.